In this PDR video, we are going to cover the mission objectives, the rocket performance during flight, and the design of our propulsion recovery airframe and our structures and avionics subsystems. In the mission objectives, we want, of course, to fulfill the requirements of the competition, which is to carry a 4-kilo payload and also make a rocket that can reach 3 kilometers apogee. But in addition to that, we also want to bring innovations to the rocket design and competition fields. These innovations, in our case, are going to be the design from scratch of an L-class rocket motor, 5 independent electronic systems, and a double recovery system. Well, here on rocket performance, in the aspect of drag effectiveness of the rocket, we are able to notice that the nose cone has a sufficient performance in the overcoming of drag due to the chosen LH design. In the right upper corner, we are able to see that the transition between the laminar flow and the turbulent flow is presented at sufficient levels for stable flight. As for the analysis of main drag areas below, we are able to see expected and manageable drag forces over the tip of the nose cone, some areas along the fuselage due to screw fixation, and behind the fins due to common base fin drag vortex. Regarding height, speed, and acceleration, we are able to see a standard behavior for a rocket of its kind. The apogee is reached at 25 seconds of flight, at the same time in which the pilot parachute is released, which considerably decreases the rate of descent of the rocket until it reaches 500 meters, when the main parachute is released and the rate of descent is lowered even more, so the rocket can be recovered safely. In addition, the measurement of vertical speed in blue has also an exponential growth throughout the motor burn follow, which is then followed by a rapid decrease until the opening of the pilot parachute, moment in which the rocket finally starts its descent. The rocket engine is based on a solid KNSP propellant, potassium nitrate, and sorbitol. It was designed to operate at 550 psi, generating an average thrust of 1,274 newtons during approximately 22.6 seconds of burning. The engine rating is L with an impulse of 3,710 newton seconds, and its carbon fiber design leaves it only with 1.8 kilos when empty. The material of the dome is 1020 steel, and the other components are made of aluminum. The carbon fiber is computed to withstand 3 times the pressure and work at a temperature well below the combustion temperature during engine burning. The temperature of the carbon fiber is stabilized by the insulating layer between the inhibiting paper and the fiber. The rocket will be 2 meters long and 8 centimeters of external diameters. Its fuselage will be made of fiberglass biaxial fabric type S. The process consists in widening the fabric around a 7.7 outer diameter PVC tube, which will be greased in release agent. It will be given 5 turns to acquire the necessary resistance, and throughout the process, epoxy resin is manually passed. After that, we wait 48 hours in a place without humidity for the cure of the tubes. And for the nose cone, we'll use the same fiberglass sheets, and the process will be the same as the fuselage, but we will use a mold of printed PLA. The fins, however, are made of trapezoidal cuts in a 1 mm thick aluminum sheet, and they are attached to the rocket's body through a fins guide made out of 3D printed PLA. In our rocket, we have 5 avionic devices. One main board that has the data from the accelerometer and the gyromagnometer, the barometer, and the GPS, and that transmits data from the rocket to the ground. 2 self-made plates for the pilot and main parachute activations, 2 COTS solutions, one is the RRC+, and the other one is the pion altimeter. Each circuit is supplied by its own battery and works independently. The recovery of our project consists of a double ejection system with a 60 diameter guide parachute released at the apogee and another 1 meter diameter parachute which is released about 300 meters from the ground. The first ejection state consists of a pyrotechnical system equipped with 5 grams of gunpowder. The expansion will expel the first parachute, which due to its small size will reduce the fall speed to about 13 meters per second, enough speed to allow the rocket to go down without staying too far from the launch site. The second ejection system consists of an electronic system that will be expelled by springs with its potential release after activation of a servo motor. The stage will reduce the fall speed to around 8 meters per second, bringing the entire structure safely to the ground. So this is the PDR video for our Hórus project. We hope all the information needed was covered, and thank you very much.